recording and maybe it'll actually freaking work.
So this is the first one in your series?
This is number one.
Candid camera.
And if you guys see that it stops recording or something, let me know.
Do you want to flip the screen around so you can see it?
I don't know that I can actually see it, but this is an ancient camera. But anyway, there we go. Now I got to be all self-conscious because I got to look at myself.
Well, you can see if you're in frame now.
So we're going to do basic circuits, electricity, and we'll lead into electronics. And we're going to cover safety tonight. We're not going to do this all tonight. It's going to be a series. What I'm thinking is that we'll kind of do baby steps, but then I'll end up into sort of microcontrollers, because that's what most people want to do here anyway, right? We want to get blinky lights and shit that does things and remote control cars. And then as I walk along through microcontrollers, what we'll do is like simple basics of code. There's persistence of vision tricks that you want to do, and then we'll go into, like, just as an idea, if you look at a microcontroller, it has a computational core, and it has all these peripherals around the outside. You want to use each one for a different thing. So we might do something where we say, oh, okay, well, let's use this kind of peripheral and do some code and maybe explain what it does, maybe give you some homework so you just go off and practice something and get an idea of it, come back in 2 weeks or a week, whatever we decide is the right spacing for the classes. We can talk about what you did, then move on to the next one, right? And start to give some ideas. So, now this gets weird. There's a chicken and egg thing here. So I want to talk about safety. But some of it doesn't make sense without some of the basics. So I don't know which one to do first. So we'll talk about some of the basics. Electricity is the movement. I'm going to lie to you a lot, just to simplify things, right? So let's talk about a piece of wire, a piece of copper laying there, right? It's sitting here. It's got full of atoms, right? We know the whole world's made out of atoms. And copper is an ion, and if I remember right, it's got like an extra electron sitting here. And you've got what amounts to extra electrons, and we can go into physics classes and show valence and valence bands and band diagrams and all this kind of shit, and potential diagrams, and we don't care for this, right? What you got is you've got an electron, an electron, an electron, and at one end you stuff an electron in, and the other end one pops out. Or that's electron flow theory. The other is whole flow theory. So some of your conductors have an absence of electrons, and they have more holes. When you look at your classical Bohr model of an atom, right? You got your is that right? 4, I think. You got your electrons floating around in shells, right? This is probably what we learned in high school and grade school. An absence of one is a hole. So the same thing happens, right? I can push a hole in, and the hole pops out the other side. What's really happening is this electron's falling into this hole, and it's pushing one out, and it pushes over here, and a hole comes out the other way. It doesn't matter. It's the same thing, it's just a different way of looking at the problem. All the math is exactly the same no matter what you do, as long as you stay consistent. If you flip your ideas in the middle, it doesn't work. So I'm going to stick with all of this, what's called conventional current flow. This is what Ben Franklin came up with in whatever year that was, 1700 and something. And it's electron flow. And we're going to say, which is even more wrong, it's actually, I'm telling you a lie there too, it's whole flow. You have a battery. This is the symbol for a battery. The big one is the positive plate, the little one's the negative plate. And current, if I just strap a wire around it, current flows this way. Units. There's four basic units. The first one is a battery, has voltage. You can see it as a V. You might also see it as an E. E is electromagnetic force. That's what it really is the electromagnetic force. The current flowing around is I. And this symbol is a resistor, R for resistance. Its unit is in ohms. Currents is in amps. Electromagnetic force is in volts. It's an ampere, actually. And that's an ohm. The last one that's left is P. It's power. And it's in watts. These are all named after guys who did a lot of founding work at the beginning. These four things are your base. It's the core of everything, of simple circuits. Everything's dependent on these. These are all dependent on each other. They're completely independent. You change one, you change one of the others. So let's take a step back. Piece of fun history. This symbol actually represents the plates in the chemical reactor that is a battery. It used to be, if you can find some really old schematics, you'll see that somebody in a AA battery, for instance, it's like 1.5 volts, right? So you have one plate and one anode, or one cathode and one anode, and that's 1.5 volts. If you had a 3-volt supply, it would look like this, and they would actually do in each one. And if you had a 1,000-volt supply, they got fed up, and I think the most they ever did was like 5. And above that, it's like, forget it. And then they'd write out here on the side. So for a battery, this is specifically a battery. What we generally will use is a voltage source. This is just a generic voltage source with a connection on either side. Nice and easy. Now, there's some basic stuff going on here. Conventional current flow. Current flows from positive to negative. The first rule is Norton's law, Norton's current laws. I want to go there. Yeah. So these all fall from the laws of thermodynamics. And the first law is energy can be neither created nor destroyed. It can change form, but you can't get rid of it, you can't make it. So what it says is, the first one is Norton's law, that the sum of the currents into a node. So let's talk about a schematic real quick, right? I'll draw, there would be a volt, there's different pieces. The schematic is the visual representation of the circuit, just for easy drawing. Just a line represents a wire. I'm lying, it has no resistance. The truth is it has a really, really small resistance, but generally in most things it's small enough that you don't care, that it doesn't matter. So a dot on the schematic means that these three wires here are connected. Good practice is to never do this, because it can get confusing, especially in print. Sometimes you don't always see the dot. If you see that, that just means those two wires cross. They're not actually connected. In really old schematics, whenever you had two wires cross, you'd see this. And that let you know that it jumped over, but you don't see that real often anymore. So good form is not to run a dot through the middle, it's to do this and come off separate so that there's no ambiguity. You look at it, you know. People disregard that rule and do it anyway. But so Norton's current law says that the sum of the currents entering a node, this is a node, and the sum of the currents leaving the node must equal 0. So if I have I1, I2, and I3, that says I1 plus I2 plus I3 equals 0. And a sign would be direction, right? So if I say going into the node is positive, just for shits and giggles, well, when I solve this for I3, what's I3 coming out right away, right? I subtract I3, and I subtract I3, and now I've got I1 plus I2 equals minus I3. These two are going in, that one's going out. That's all it means. The next thing is, we'll simplify this, that the sum of all voltages in a loop has to equal 0. So if I were to start here, and I call this my reference point, and that's what this symbol means, loosely ground. Ground is means a lot of things depending on what you're in. So we're just going to use it right now as our reference. Ground is your reference. If I start at ground and work my way around, I've got some voltage V minus the positive, so I get negative V. And then I've got some voltage here. I'll call this V0 and V1. Plus, so V0 plus V1 equals 0. That effectively means in this simple circuit, since there's only one, V0 equals V1. I think that's simple enough algebra. I don't have to do the adds and whatever. If you want me to, I will. So, slightly more complex then, right? I get another device here, and now it's got plus or minus V2. And so now V0 equals negative V0 equals positive V2 minus V0 plus V2 plus V1 equals 0. So V2 plus V1 is equal to V0. Right? You're looking really hard. Am I making sense?
I was thinking about a different equation, but I was thinking you're going to get to it. The
Ohms Law?
V equals I over R and all.
Ohms Law.
Variance.
Oh, sorry.
Okay.
Sorry. So
No problem.
so the-
Okay,
so you
let's
said
do
the
this.
first-
Ask questions at any time.
Oh,
Okay.
Ask questions at any time, because I don't want to miss it. And if you're smarter than me, some people are, and you've got something to add to it, and we can have a discussion, right? This is, so
All
go
right.
ahead.
All right. So the first law, where you're calculating the current at each node. That was called Norton's current laws, but the second law,
Kirchoff's voltage law.
Kirchoff. Okay.
Kirchoff. Kirchoff. I've also heard it pronounced Kirchoff. I learned Kirchoff. I don't know what the right way is. If you hear somebody else, maybe I'm wrong. I don't know. Never, yeah, you never make fun of somebody when they say a word wrong, because that means they read it somewhere and they've never heard it right. So, all right, so let's talk Ohm's Law. I'm gonna make it easy right here. Let's get rid of some of the marks.
someone taught me this electricity was like water.
It is, and I'll get there. I've got some, whoever said that.
Yeah.
I've got analogies that'll go with this. They go with all the different a lot of the different components, not all of them. So, I just want to get this far so that we can get to safety, right? The voltage at these are, like I said, these are all dependent on each other. So voltage is equal to I times R. Now in a simple case like this, you know the voltage can't change, right? I mean, there's nothing. If I've only got these things, the only thing that can change is I, R, or V. But if I hold one of them constant, so if I say this is a 5-volt supply, my Raspberry Pi runs off of a 5-volt wall wart, right? So if I've got a 5-volt power converter, that's 5 volts. So now it all depends on R. If R is 10 ohms, I equals V over R. So 5 divided by 10 is 0.1. So I've got 0.1 amperes, 0.1 amps. I think volts is actually Volta was the guy's name. There's a easy, I'm trying to remember if I can, it used to be a triangle, and it was
Yes, sir.
VIR like this.
I just do the same thing.
So V is equal to I times R. R is equal to V. You do the rearrangements. R is equal to V over I, and I is equal to V over R. Simple triangle, right there.
Like if you have two of those, you can always find the third, right? By
Yep.
making some equation.
Yep, and this is the equation right here. E equals IR. And this is Ohm's Law. The next fundamental thing is power. We talked about power. Anything you do, you're changing forms of energy. Most of what you do when you change your forms of energy is you make heat. Power is equal to current times voltage. I shouldn't do that. That means something in matrix math. IV. So now we can throw that in there and you can find any of the others, right? So I say, well, P is equal to IV. Well, this is easy. We know this is 5 volts here because that's the only device in the circuit. And its I is, what did we figure it out, 0.5 amps. So P in this circuit is 5 times 0.5, which is, I think, 2.5 watts, right? 5 times 0.5, 5 times 5 is 25, and the decimal 1 point, 2.5 watts. 2.5 watts is a lot, that'll burn your finger. We don't have them much anymore. Incandescent light bulbs, 100 watts. It's 100 watts in this much space, gets dang hot. 2.5 watts in the size of a resistor, gets dang hot. So when we get into doing our projects, that's something to worry about. Now, this is something I wanted to bring up safety-wise. It's interesting. The National Electric Code, which is the code that you're supposed to follow when you wire buildings and houses and businesses and whatever, it's actually, I want to say part 40 of the National Fire Protection Act. Our code for electrical wiring for buildings is part of the National Fire Protection Act. And the reason is, back in whenever, people were burning down houses, wiring up the first electric canal. You've got to come up with something like this. And it was treated as a building thing. So NEC code says this is how you'll do these things. It's evolved over the years. It does this. There's also another part of the NFPA, Part 70E, I think, if I remember right. And that is, it's like the National Electric Code, but it's for businesses, warehouses, shop floors, things like that. There's some subtle changes to it, and it works more with some of the bigger voltages, right? So we've talked about this, so let's talk about safety real quick. This right here is, you can find this online. I'll hand it around if you want to take a look at it. It's 45 pages. It's real easy. It's a PowerPoint presentation put together by OSHA on electrical safety. So if you want to look at it, look at it. But what it comes down to is this. So the resistance of the human body is generally along these lines, hand to hand. If you are dry and not wet, it can be like 500 ohms up to like 500 kilo ohms. So when you get yourself in this circuit with 5 volts, there can be a little bit of current running. There will be current there. Usually it's microamps, not enough to notice, but there's current there. Now,
The ohms you would think of as the valve, right?
okay,
The
well,
water valve.
sure. Okay.
Sorry about the analogies.
No, you're fine. You're fine. So voltage is pressure.
Right.
I've got a water tower out here, right, with a big thing of water on top, and a pipe coming down. I pump that stuff up high enough in the air, it's got a lot of pressure behind it, right? So, or if you want to think about it as being a water pump, you can call it a water pump. We can think of the wire as being a hose. The bigger around the wire, the less resistance to the flow of water it has. That's a perfect analogy. The resistor would be if you got a pipe this big, it's like a section of pipe that's smaller. It resists the flow. That's what's going on. It's a little different than water though. Electrons are going to move at the same speed,
Yeah,
regardless.
because
There's
water
just
will
going to be
speed up in that.
right. Well, you'll get a high pressure here,
Right.
and you'll get a low pressure there as it shoots through.
But
And then it'll be, if this is tank, right, like in a hydraulic system, then that's going to be zero pressure right there because that's going to be your reference level.
but for the sake of electricity.
For the sake of this, so what happens here is water comes around and it actually slows down here, speeds up through the venturi, and then kind of does whatever it does after that. Electrons flow at the same speed. That voltage potential says they're going to flow at this speed, and it's called the drift current. But what happens is fewer of them go through it, or it takes them longer to go through it, which is not the same as slowing down, right? Generally, when I drew the picture earlier where they just kind of go right on through. Well, instead, maybe they have to go this way and bounce around, and it takes them a while to get through because they have to do this screwy path. Old resistors were carbon, and they just stuff it in there, and the 2 wires would come in, and it had to jump from a piece of carbon to a piece of carbon, and it just kind of took the
But our bodies always have certain resistance.
right. Don't
Don't try that.
Is that the
All
amount
right.
before you die?
yeah. So we'll talk about water. Everybody's the truism that water is a good conductor. It's not. Pure water is not a good conductor. There's no such thing. You don't have to put very much in it to make it a pretty good conductor. Your body's full of dirty water, right? So your skin has is an insulator. An insulator is something that's got a really high resistance. It keeps, we wrap our wires in plastic, right? Teflon, nylon, different stuff. That keeps them from being able to just touch and make a metal-to-metal connection somewhere and have current go where you don't want it. But it has a breakdown voltage. If you get high enough of a pressure on it, hey, it's going to rupture that valve and go right on through, right? It's going to rupture that membrane. It's going to blow a hole in the hose, even though you got it turned off, and then it's going to be water everywhere. On your body, if your skin is dry, and the drier you are, so in the wintertime, you probably have a higher resistance. In the summertime, when you're sweating and you got salt and water all over you, you got a lower resistance. So, this is a lie, but it's not a lie. This is how much current it takes to cause each one of these things. Now, there's something called alternating current, which we see on the wall outlets, and there's something called DC current, direct current, which we use in our projects. Direct current never changes value. right? So it is, if I look at it in time, so if I make a chart where this axis is time, and this level's voltage, this axis is voltage, what I'll see is DC current is always this. If I talk about 5 volts DC, it looks like that. In time, it doesn't change. If I talk about, I'm going to use 120 volts AC, because that's what we're all familiar with, what it looks like is this.
Is it going negative?
Yeah. And it's actually, at the peak, if I remember right, 170 volts. But the 120 volts, it's 170 volts peak. It's peak to peak. No, it's peak. It's 120 volts RMS, which is the root mean squared, which means it's the root of the mean of the squares. So you take this over this amount of time, and what that tells you is that's the equivalent DC voltage. 120 volts AC is really 170 volts at the peaks, but it has the same amount of energy to it as a 120 volt DC signal. Because you've got all this dead time where it's less than 120 volts, right? And it doesn't matter which way it's flowing, it's flowing. A lot of AC things, instead of that electron just going through and pooping out the end, they poop them back and they poop them back. Back and forth and back and forth and back and forth, and you're basically taking the energy away from that movement. Kind of like a wave action, right, at the beach. You can make a generator out of it. Same kind of thing, only now you're using imaginary numbers, which I won't go into too much, especially not today. All right. So, as an aside, you hear your wall outlet here in the US called 120 volts, 110 volts, and 115 volts all over the place, right? Everybody calls it something different. The reason for the confusion is at the wall, where at the entry point, like right at the meter, coming in from the utility, it's 120 volts there. The maximum drop allowed on any one leg of your circuitry after your fuse box is down to 110 volts. So you're guaranteed for it to be at least 110 volts, no matter where, if your house is designed right or your business is designed right. But it could be up to 120 volts, and just people call it 115 volts because at any given place it's probably going to be around 115 if you measure it. It's all the same thing.
And what's the drop from? Is it the resistance of the wiring? Or?
Yeah, so you're putting enough current through the wires that a small resistance at that point makes a difference. And if you want to get into that kind of thing, power wiring, you actually, if you go online and Google AWG table, American Wire Gauge, you can find tables that say, for power wiring, if you're going to have this much current in the wire, you have to use a conductor that's at least this gauge. And those are kind of conservative. They're not real conservative, but they're kind of conservative. So if you follow those, it's good. I think the normal circuit you'll see in a house is like a 20 amp circuit usually. And if I remember right, that's like 14 gauge wire. The smaller the number, the bigger the wire. So a 20 gauge wire is, it's about that big around. It's the stuff that you use when you're wiring up your Pi. It's those jumper wires on your Arduino kit. 14 gauge wire is about that big. And then it goes 14, 13, 12. Most often you see even numbers. You don't real often see odd numbers until you get up into the big stuff, and then you get to see like 4, 3, 2, 1, aught, 0, double aught, triple aught, quadruple aught. And then a double aught wire is a battery cable on your car. It's about that bigger. It's about big around as my pinky, a little bit smaller. a triple aught, a 4-aught is about that big. And I mean, about the size of my thumb. And if you're doing solid copper, it's hard to bend and move around. And then above that, they go to KC mill. So it's K, which is 1,000 circular mills. So a mill is 1,000th of an inch. Maybe we should go over units real quick as far as the Greek units.
Okay, so you can think of the gauges as that would be in the impedance figure, or of the resistance, or neither of them?
It is directly related, but it depends on the material the wire's made out of. Because there's aluminum wire, there's copper. For that, there's aluminum wire, and there's copper
Like
wire, and
copper
there's stranded
wire.
copper wire.
Okay, I just wanted to think of what the gauge, where that fit in with that, with
The
the resistance. or-
bigger the gauge, the smaller the wire, so the higher the resistance. So if you look at the wire from the end, and you're pushing electrons into it, well, electrons repel, right? So they tend to run around out here on the edges, and the smaller it is, the less room there is for them. And then what's left starts to move down in the middle. This is actually called a skin currents, skin resistances, things like that. So I mean, you get into it. There's all sorts of crazy physics in there that I can't even explain, but it is the way it is. And
But you go to AWG, they'll give you guides to know what gauges.
just search
for how much
search,
juice you're going to push through.
search AWG table.
Okay.
There's a couple. There's like one that I always go to because it's got a really nice table, and it tells you the AWG, the American wire gauge. So 4/aught, 3/aught, 2/aught, all the way down to like 40 gauge, I think, which is like hairs, down to like 40. And then it has a column that tells you, and some of them also have KC mills here. So it'll have, I think the first step is like I want to say it's 200 KC mill. And then it has the, some of the tables will tell you circular mills. A mill equals 1/1000th of an inch. So that's the circular area. So when they talk circular mills, pi r squared mills. And then they'll tell you sometimes the diameter, and they'll tell you sometimes, it depends on the table. You can see the skin resistance at a frequency, which matters. Again, that sinusoid we were talking about here, 60 hertz, 60 cycles, 60 full sine waves per second. But I mean, RF is gigahertz, right? It's millions of cycles per second. It'll give you, some of them will give you the like pounds per foot, and then ohms per usually 1,000 feet. And some of the tables will give you.
Why is that? Is there the longer the run, do you lose?
The longer the run, the more resistance.
I'm just thinking from a computer networking standpoint.
Yeah.
But I didn't really translate it until you wrote that down. Huh? Yeah, never thought of
Yeah,
that.
that's-
Electricity itself. Yeah.
Mm-hmm.
Yeah, the resistance comes from how hard it is. If I have a block, I'm going to use a square because it's easier. If I have a block of material, right, the resistance is defined. It's defined by the area. So if it's rectangular, you got a height times a width. So it's height times width times rho, which is the resistivity of the material, and its rho is usually in ohms per meter. So rho is resistivity and it's ohm meters, ohms per meter, ohms per. It's not quite right.
But that'd be for different materials like copper.
It changed. Copper's different from aluminum. It's
Silver,
different from
whatever.
silver, from gold. Silver is actually the best conductor.
Isn't that interesting? This just costs so much, so they can't.
Actually, copper costs more these days,
Does
but silver
tarnishes.
corrodes.
Yeah.
Oh.
Silver
Can't
corrodes, and
maintain
if you get a
fire.
corrosion joint, that's even more resistance, right?
Yeah.
And now you start a fire there.
Gotcha.
Yeah.
Gold is actually, we use gold plating on everything because gold is not quite as good as silver, but it doesn't corrode. It's noble-ish.
Alright, so if the resistance builds as it gets longer, and you also have the drip current principle. So the maximum length. So like say you have a set voltage, there has to be some maximum length that the wire can be in order for it to.
Based on the load,
Okay.
based on the current you want to draw through it. So I'll do a quick. They'll do a max current for power distribution, and they'll do a max current for chassis wiring. So and there's some other things you can see. So the difference between those two is the assumptions. So, okay, we talked about power as a watt, which is watts translate directly into thermal energy when you're talking resistance. That's how a space heater works, right? You plug it into the wall and it gets hot. That's the perfect example of that. It's a fairly low resistance, but it's a lot of current. I squared R, right? When you go back to the V equals I R, P equals I V. So if I solve for V,
Or if you substitute V, then you just get
right,
I squared.
V equal, yeah, there we go, thank
Squared
you.
R, yeah.
Thank you. I squared R. So when you're, the assumption is one has more cooling capability, right? It's out in air, it can have airflow over it, it'll get hot. And then depending on the environment you're in, I do stuff right now, sometimes it's on ships. So the insulation has to be saltwater resistant, it has to be oil and hydraulic fluid resistant, and so that puts you into certain kinds of materials.
Plenum?
Yeah, it's
Plenum?
heat resistant, yeah.
Is that the stuff? I don't know.
A lot of what we use for small wirings, Teflon or
Oh.
Kapton.
I think the plenum was a heat resistant
Well, plenum is
or-
the hole through the wall. To me, it's a plenum ceiling is this whole area is above it is open for airflow. So
Oh,
I mean,
okay.
it's multiple meanings.
Oh.
There's different polyester type stuff that they use. There's actually polyvinyl chloride. It's the same stuff that you make out of
Yeah, PVC.
PVC. It's slightly different mix, but
Yeah.
they all have their appropriate uses and not uses.
Yeah, I guess the context I've heard plenum used in is network wiring, and they call it plenum, and I was always told that was like heat resistant and all that. But I guess it's
It's
just
really 'cause they're just running it through the
wiring
ceiling.
meant to be used in the ceiling. Yeah, so it's not that wasn't
Yeah, so there's and some of the different stuff is right. Certain materials of the resistance materials, their resistivity, their insulation resistance starts to go down at a certain temperature, or it starts to fall apart. So if you go into the NEC, the National Electric Code, Part 40, I think, of National Fire Protection Act that we talked about, that goes into, they've already done all the calculations. It's like somebody was telling me last week working on the mill. You know, you can go figure out how you break a bit and what your bit speed ought to be for a travel speed and everything else. Or you can just go to a table that they've already calculated, and there they have, hey, if you've got this much current and your in air, you don't have a big stack of wires stacked up. You can use this much current on your stuff with certainty ratings for outside temperature, and your wire won't get hotter than this, which is loosey-goosey. You find that a lot of it, they run, for commercial stuff, it's amazing. They cut all the way to the bone, and they get rid of most of the margin. The wiring inside of your wall, if you put it at full load and it's the full length that you're allowed to go, that wiring can get like over 100 C, it can boil water. But it's not hot enough to start a fire, right? So then it becomes a different safety issue. Is anybody going to be close enough to it that they can burn themselves on it?
Oh.
So, all right, so let's go back to this resistance between two different points. This is a lie because your body acts slightly differently to AC than it does to DC. So the first thing that happens is, you ever stick a 9-volt battery on your tongue to see if it's still alive?
Yeah.
It kind of burns and it tingles. Mm-hmm. You're down here somewhere between 1/2 of a milliamp and 10 milliamps. Let's do units real quick because these are all over the place. Let's see. Start down here. Pico, nano, micro, milli, unity. So this is 10 to the 0. This is 10 to the -3, so 0.001. These are milliamps, milli whatevers. This is X. What's the right way to draw this? Let's go here. We've got unity, milli, kilo, milli, micro, nano, pico, actually femto, I want to say atto, but that might be way the hell up there.
Do many things go that small?
Yep.
Really? Okay.
Yep.
A little smaller, a few.
Yeah,
Keeps
it's
going.
below femto. It's, I can't remember. It's atto.
There's like neutrinos, right? And then even smaller than that.
Well, we're talking just base units, right? So then we got kilo, mega.
Practically speaking.
Yeah.
Notice milli is a small m, mega is a capital M. Giga, unless you're the professor in Back to the Future, in which case it's giga.
Gigawatts.
Kilo, mega, giga. So this is
Tera.
thousands. Thousands, millions, billions. Giga, tera, T is tera. 2 R's? I think it's only 1 R. Tera,
Yeah.
trillions. Comes above tera. Tera might be
Peta.
Peta. Peta amps. Whatever is above trillions, that's 100 trillions.
Quadrillions. 1,000 trillions.
Is that quadrillion? Yeah, I think so. Yeah,
Something.
quadrillion.
Anyway,
Quadrillion.
big numbers.
And then up. There's more. Practically, you never get out of these. So 10 to the 0, 10 to the -3, 10 to the -6, 10 to the -9. That's an, not an R. That is an N.
And
10
the
to the
micro is
minus-
like a U shape, right? Like a.
It's
a
this.
mu.
It's a Greek mu. It
Yeah.
comes up like that.
Yeah.
Mu.
That's what the Zen.
And 10 to the minus, so they're by threes. 3, 6, 9, 12, -15 is femto. Pico you'll use doing electronic design. Femto not so often. So kilo 10 to the third, mega 10 to the sixth, 10 to the 9, 10 to the 12, 10 to the 15.
You would use for amps in electronic design?
What's that?
You said pico you'll use in electronic design
All the
for
time.
amps? Or for what?
Capacitance, which we'll get to, but not probably, maybe not tonight. It just depends, because we've already burnt an hour, and we haven't even got to freaking safety yet. But we've gotten through a lot of the basics.
They're pretty safe.
So let's talk. So again, let's get back. So 1 volt into 1 ohm is 1 amp, and it's 1 watt. All unity. They all fall to unity together. 1 amp. You say, well, that's not much. It's 1 amp. 1 amp will kill your ass dead. Okay. And what you'll hear people say, and what you'll see in some of the stuff is, oh, it's not the voltage that kills you, it's the current that kills you. Well, bullshit, they're all interrelated, right? But once it goes into your body, it is the current that kills you. So this is the slightly more conservative. This is where I think you start to feel AC stuff, because AC, so your heart beats on its own, but it's got a signal that comes from your brain that every now and then says, a little metronome that says, you should fire now, and then it bang, 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 bang. It says, you should fire now, bang, 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 and it resyncs. So you've heard of fibrillation, the defibrillator? What happens is your heart goes and just starts, it loses all sync. And what a defibrillator does is it puts enough current through you to compress it, make it stop, and it sits there and does nothing for a second, and then it gets that next pulse, and thinks, oh, okay, bang, 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 bang.
That's just 100 milliamps.
100 milliamps.
Oh.
So, if you bridge there with a 9-volt battery, you're going to feel it tingle. If you bridge it with the wall, you're going to blow your tongue off. Quite literally. It'll cause burns. If you accidentally grab hold of the wire and it goes this way, this has happened to me before. There's actually, it was when I was a kid, I think it was this way. It went from that heel to this hand. So it went whatever through, and it was above 10 to 40 milliamps. That's the let go threshold. That's where there's,
Is that where you firm up and?
that you
That's
can't
why
let go.
Some electricians carry around I used to talk to some electricians and we carry around a wooden bat with us
To knock you off.
to knock them off because
So
It doesn't conduct.
it doesn't conduct.
I don't want to make you afraid of electricity. All right?
You sure?
You should have a healthy respect.
You should respect it. People who get afraid of shit, then they screw up whenever they're around it, right? Because they get all twitchy and whatever. Respect it. It can kill you. It can hurt you. So, you know, a half of a milliamp down here, so that's 500 microamps, to 3 milliamps tingles, and I felt that multiple times. 3 to 10. Did you do the lab in high school where you got the frog and you stick the voltage probes on him and his little flippy leg goes like this? That'll do that to you. But I want to see the day when somebody's doing some sort of neurosurgery. It's like, nurse, stand there. You know, practical joker. That's something I do. The let go threshold. You hit that, you can't let go. It completely the circuit, the signal that's being sent to your muscle is louder than what your brain can tell it to do. You can't let go. You're locked on. That's a bad place to be.
And people often try to help.
Yeah, so if you're on and I come and grab you, so if you see
Yeah, two
somebody
people,
get
yeah.
shocked,
Yeah.
if they fall to the floor, great, but you want to get them off of the line. If you see somebody hung, you need to get a wooden broomstick or something like that to knock them off. You don't want to touch them because you could complete the circuit and then you can both be stuck there. One of the training videos we got at work was, I think it was a warehouse in China. Jesus Christ. These guys, it was after hours, and they were moving a big, like a 1.5-story tall scaffolding around. It was like 4 guys that went around and it hit a high voltage line up on the side, and it hung them all. And they were just hung there. And you could actually see The one guy was starting to smoke, and they finally fell. And one guy, like, he survived it, but he had no idea what the hell was going on. He reached up and grabbed the damn thing again to pick himself up, and then he said. And these guys were there alone on a weekend, and it was all caught on the security cameras, and all 4 of them died. It was nasty. So what? Respiratory paralysis at these levels. What is it?